Welcome to Tuesday Lunch and Learn. I'm James Shore. Every week we choose a useful software engineering topic or skill, come up with a challenge related to that topic, and then solve it live on stream. And this week it's Flaky clock-based tests. If you'd like to follow along with today's episode, you can download the code from github.com/jamesshore/livestream. Check out this tag 2020-07-14. For those of you who are watching this live, do note that we are in a different branch than previous episodes. This is the clock branch. If you're watching this on YouTube, though, the best way is to, again, check out this tag right here, 2020-07-14. Your comments and questions, as always, are very welcome. Go ahead and put them in the chat. We've got lots of time today, so I'll be taking any questions that come along, and we have more time at the end if needed. Okay, flaky clock-based tests. Flaky tests are the bane of my existence. I hate them. I am on a crusade to eliminate flaky tests. Flaky tests, of course, are tests that fail randomly. They may fail in one run out of 100 or even one run out of 1,000. And that doesn't seem like such a big deal. But when you have a test suite that consists of thousands of tests, one failure out of 1,000 means that your entire test suite is failing every other run, every third run, every fourth run. And when your test suite takes minutes to run, and it's just ticking along, and then right there at the end, you get a failure, that is just not fun. So what we want is test suites that are reliable. And generally, one of the biggest reasons they're unreliable is due to race conditions. A race condition, of course, is when you have two code paths executing at the same time. Your test assumes that this one is going to complete first, and usually it does, but sometimes this one completes first. And clocks and time are a really common source of race conditions. Specifically, clocks tend to lead to slow and flaky tests because you'll often use clocks, or you also often have time in your tests when you're having some sort of timeout. Maybe you want to wait a few seconds for something to finish. You've got a timeout in your code that's waiting to see if something is going to finish on time. And so your test actually waits those few seconds. Well, that's really slow. We don't want to do that. And even when you do that, even when you have your test wait, your code doesn't always finish in exactly the time that you think it will. Sometimes your computer takes a little bit longer. My computer every so often decides to spin up my external USB drives. Every time it does that, the whole system freezes for 3 seconds. And if I was doing a test at that moment that depended on the system clock, that test would fail because none of my tests expect a 3-second delay. So computation time is non-deterministic. Also, assumptions about your test are not always true. You write your test and you assume, and you're trying to write a good solid test. So you'll say that, let's say you're printing today's date. And in your test, you say, well, today's date is date.now and then whatever. But sometimes your test is going to flip over. It's going to run at midnight, and your test is going to flip over, and it's not actually today's date. And now your test fails. Or maybe you're assuming that you're in a month that has either 30 or 31 days, and you forgot about February, or if you forgot about leap years, or there's any number of things. You can look up online. There's actually a story of a program that only failed once in a blue moon. A blue moon is the second full moon of a month, and it literally failed in that situation. So we don't want to have that. And that is what today's episode is about, how we can prevent these slow, flaky tests. Specifically, the challenge that we have today is we're going to write a little toy application, a countdown app. It's going to take an array of text strings, and it's going to print out one string at a time, waiting 1 second between each one. So if we provide an array with 5, 4, 3, 2, 1 in it, then it will print out 5, wait a second, print out 4, wait a second, 3, 2, and 1. This is a toy application. It's really easy to write. The challenge here is not writing the application, it's writing it in a way that has high quality tests, robust tests, and not flaky tests. So that is our challenge. I'm going to let you all cogitate on that for a moment. And while you're thinking about that, I want to remind you that this show is made possible by the people who hire me for training and consulting. Typically, I'm hired by companies that want to have a lot of business agility, but don't have the technical capacity that they need to achieve that business agility. It tends to be lower bureaucracy companies that are interested in innovative ways of working. Also, not gigantic technical organizations, typically less than 500 people in the engineering organization, which is still not tiny. You can go ahead and email me at jshore@jamesshore.com or visit me on the web, jamesshore.com. I work with anything from one team to many of teams. If you'd be interested in talking to me, go ahead and send me an email. I'd be happy to set up a free consultation. I also welcome anybody for any reason at all. Go ahead and send me a tweet at James Shore. Okay, let's get back to the challenge. We are going to be building a countdown app, and we're going to do it with high quality, fast, and non-flaky tests. How are we going to do this? Okay, the solution here is basically to control the clock. So waiting for timeouts is slow. So what we're going to do is we're not going to wait for timeouts. We're going to force the timeout to happen when we want it to. Computation time is non-deterministic. Fine. We will have a clock that is not based on the system clock that is deterministic. Things happen exactly when we say. Assumptions about today don't always work tomorrow. Well, we're going to control what now is so that it never changes and it is exactly what we think it is. We want a blue moon. We will program in a blue moon. Specifically, the way we're going to do this is with an old standby infrastructure wrappers. And if you've been watching the show, you know that we've covered this before. If you haven't been watching the show, you can find back episodes right down here, jamesshore.com/blog/lunchandlearn. And they're also, the specific episodes I'm talking about are also referenced in the README, which you, again, can download from GitHub. I'll share that link again in a moment. So we're going to create an infrastructure wrapper for the system clock, and we're going to call it clock.js. And that is going to use the globals of date and set timeout, which in JavaScript, which is the language we're using today, in JavaScript is how you deal with the system clock. Now, once you have that infrastructure wrapper and you have the system clock all sort of wrapped up in code that you can control, now you have several options. You can use null objects or other test doubles in your test to control how that wrapper behaves. Or, as I prefer, you can use nullable infrastructure. That's what we're going to do today. We're going to make our clock infrastructure wrapper a nullable infrastructure wrapper, and we're going to have it work the way we want when we're using our tests. Normally, again, you can find information on this particular information about nullable infrastructure wrappers in the Testing Without Mouse episode. Again, that's here at this URL. Normally what we do is we use an embedded stub and we write that ourselves because we're just writing a little bit of stub code. But for clocks, it's actually complicated enough. We need a full-blown fake clock that can handle timeouts and timers and stuff like that. So rather than writing that ourselves, we're going to follow Larry Wall's 3 virtues of the Perl programmer. That's laziness, impatience, and hubris. Specifically laziness. I am too lazy to write a fake clock myself, so we're going to use a third-party library from Sign-On called Fake Timers. So that is what we're going to do. Let's go ahead and get to it. Again, if you'd like to check out the code, you can get it from github.com/jamesshore/livestream. Check out the tag 2020-07-14. At the end of the episode, I will check in the finished result with the tag 2020-07-14-end. As usual. If you'd like to follow along, we are going to be programming in Node.js. This does apply to any language, any modern mainstream language, but I'm using JavaScript and Node.js. So if you'd like to follow along with the code, you will need Node.js installed. Once it's installed, you can build, lint, and test the code by using build.sh. And you can have that build only lint and test the things that have been changed by providing the quick option. And you can automatically have it run automatically by using watch. And that will also make a little sound like that when the tests pass or fail. To run the code, use /run.sh, or all of these can be done with just run or build or watch on Windows, and that will run the code. But there is no code yet, so it's just going to say to do. Now, let's go ahead and get started with this. Here is our countdown code. You can see that it takes a text array for us to do something with, and then it just writes out to do to standard out. Now, again, implementing this, not a big deal. Our real challenge here is doing this in a way that is going to give us good, high-quality tests. Specifically, I want to create that nullable infrastructure wrapper. So I'm going to set aside our countdown app, and we're going to go into the infrastructure directory, and we're going to take the clock test and clock that I've already created. These are just stubbed in. There's nothing in here just yet. So let's see these run a test. Okay, there's our test running. Okay, so first thing we need to do, I think, with a clock is have some way of knowing what time it is. So getting the timestamp back. So we'll say that it provides a current timestamp. And to do that, we'll need to create the clock. And following the infrastructure wrapper pattern that I prefer in JavaScript, I'm going to use a factory method called create. In other languages, you don't have to use create, but in JavaScript, because we don't have private constructors, this is my preference. So we'll do that. That is going to fail because we don't have it. Then I'll add a static create method and return a new clock. Okay. Now what we need to do is we need to get the current timestamp. And I'm going to use now for that because that's a nice value. And we'll say that the actual time is clock.now. And then let's expect that that is going to equal whatever the real system clock value is, which is in JavaScript done with date.now. That's going to fail because we don't have a now function. Can add it. Now they'll fail because it's returning undefined. You can see that right there. And then we can return the actual date.now. And there we go. Now we have a little problem here. We want to create tests that aren't flaky. And the way we create tests that aren't flaky is by creating tests that don't actually deal with the system clock. But we're creating an infrastructure wrapper. And in order to know that that infrastructure wrapper actually works, we need to test it for real, which means talking to the system clock. So now we've got flaky tests again, because these could happen in, there could actually be a delay here. It is possible that date.now and clock.now will return different values. Now it only takes a fraction of a millisecond for this code to run, but it does happen, and I've seen this, it does happen that the clock.now executes at the end of millisecond 100, and the date.now executes at the beginning of millisecond 101. That's a problem. So what we need to do is, rather than saying that these are equal, we need to say that the expected value is at least the actual value. And we haven't seen that fail here, and I don't think I can force it to fail, but having done many, many tests using dates, I can tell you it does happen. Something that happened in my rehearsal is I had this inlined like this. So I said clock.now equals date.now. I tend to like fairly compact tests. And that test failed. And you know why? It's because I guess in JavaScript it ran this function before it ran this function. And date.now gave me, let's say, millisecond 99. And clock.now gave me millisecond 100. And so 100 was not at least 99. So I had a flaky test. I had to break that. So what I'm going to do is I'm going to make these not be inlined. There we go. Okay. Let's try that again. And I'm going to make this not be inlined. I see some comments in the chat. I'll get to that in just a moment. Thanks for the comments, Pellet and Uncle Scientist. And to make this really clear what's going on, I'm going to say can't inline because that results in a race condition. Let's call this actual, and this will be expected. Now, some interesting comments in the chat here. Pellet says, would using some sort of double epsilon style comparison be useful too? Uncle Scientist says, assert needs is within one of or within in. And Pellet goes on to say, make sure that the actual is within a certain tolerance of expected. That is really tempting to do. And the fact is this is not a great test, because we could just implement this with return 1 billion or something like that, and it would pass, or max int or something like that. But the fact is that we can't say it's within a certain tolerance. This is what happens when people use time-based tests. They put in a tolerance to try to work around the fact that their dates are flaky. But no matter what tolerance you put in, I guarantee you the computer can exceed that tolerance, because we have no way of guaranteeing that it is going to be within 1 millisecond. It is possible to have a garbage collection cycle, a network hiccup. Like I said, when I plug in my hard drives, everything just pauses for a couple of seconds while the hard drive spins up. These things are outside of our control, so we cannot specify the tolerance. The only thing we can say for absolute certainty is that it is going to be at least the first date, because we know that the time doesn't go backwards, excluding leap seconds, which I don't think are an issue with JavaScript. That's a whole nother issue. Now, Charlie Pancake says, this feels like something that people could forget to do. Should this be a helper method of assert, like assert is same date? That is one way of doing it, Charlie Pancakes, but I actually think that this is a really low quality test. So rather than asserting, rather than working around the fact that system clock is inherently flaky, I'm going to make it so we don't have to use the system clock at all. We're going to have a few tests of the system clock in our infrastructure wrapper because we have to, and then the rest of our system, we're just not going to use the system clock. Instead, we're going to use this clock, or the clock wrapper that we control, and we're going to use the null version of that is going to be completely deterministic, unlike the system clock, which is non-deterministic. So there we have the ability to create the current, to provide the current timestamp. We also are going to need the ability to wait a certain amount of time. In our application, we're going to print out one line, then wait a second, then the next line, and then wait a second, and so forth. Now, the way that's typically done in JavaScript is that you use the set timeout global. But the nice thing about doing a wrapper is we have the ability to specify our own interface. So rather than using the fairly clunky set timeout, let's use something a little bit nicer. Let's use just wait async, and we'll wait for 10 milliseconds. Now this, of course, is not going to work. We don't have a wait async. We can implement it. And now it's going to fail. Well, actually, it's going to pass because we're running. So now we need to make the actual test. In order to do that, we're going to need to get the start time. We're going to need to get the elapsed time. And we're going to need to assert that the elapsed time is what we expected. However, as before, we can't guarantee that the wait is going to be exactly 10 milliseconds. JavaScript guarantees that the wait is at least the time you expected, but it doesn't say that it's exactly the time you expected. And let's go ahead and illustrate this. To implement wait async, we'll need to wait for a promise. And in that promise, we'll call set timeout, and have that call resolve when it's done. And we'll have that timeout after milliseconds, whatever that milliseconds value is. And you can see that, whoops, it looks like I got my calculation backwards. Expected time is clock now minus start. Anyway, you can see that that set timeout is not consistently 10 milliseconds. It was 12 milliseconds, and now it's 17 milliseconds. So again, we need to say is at least. And that is our clock wrapper. We now have the ability to get the now, and we have the ability to get the wait async, or to wait. We have the ability to get the current time. We have the ability to wait for an arbitrary number of milliseconds. But as people were mentioning in the chat, this is not a great, this is not a super exciting, this is not a great thing to use in your tests because it's so non-deterministic. So what we're going to do instead is we're going to create a nullable infrastructure wrapper. So let's go ahead and start that. So our nullable infrastructure wrapper is going to be just like the clock. It's going to behave exactly the same, except it's going to be completely deterministic. So for example, we'll say that it defaults the now to 0 milliseconds. We'll just say 0. So instead of being whatever the current time is, it will just be 0. So we'll make a null version of our clock. That's going to fail because we don't have a create null. And for now, I'll just have it return the real clock. And then we want to assert that the clock now is equal to 0. And this one, because it's deterministic, we can use the assert equal. We can say we expect it to be exactly 0. Now, this is going to fail because it's not exactly 0. And in order to implement this, I'm going to set this aside for a moment. And we're going to come in and we're going to create the embedded stub, as you've seen in past episodes. Pellet asks, do we need a test for the year 2038 problem? That is a good question. I'm not going to bother testing for that because I don't expect this code to last until 2038. For those of you who don't know, the issue is, of course, that the 32-bit integers roll over in the year 2038 on Unix. I don't know if that's still an issue, though. Is it, Pellet and Uncle Scientist? Do you know if it's actually an issue? Because I believe most systems are now using 64-bit CPUs, and they may have a 64-bit time value. I also don't know if it's an issue on JavaScript. Uncle Scientist says in Solaris, which is what he uses, or what they use where they're working, it's all 64-bit. So yeah, that should keep us going for quite a bit longer than 2038. Okay, so we need to introduce our embedded stub. What this means is that we need to pass in our globals. We've got a bunch of globals that we're using, date and set timeout. So let's pass those in to our constructor. Constructor will take some globals, save those off, and now we can use them in our code. And now that we're passing those in, we have the ability to control them in our null. Pellet says that according to Wikipedia, double precision only gives us 585 billion years. If I'm still alive when this is a problem, I will consider myself lucky. Very lucky. Okay, so now we have the ability to control our date, but we still haven't got it defined. So now we need our clock.now, which depends on date, to actually, our null version, to actually pass in a date. The way I'm going to do this is I'm going to create a set of null globals. And again, this is sort of the typical embedded stuff. So we can return an object which is going to have a date, and that date is going to have a function called now, and that function is going to return 0. And there we go. Now I could implement this all with an embedded stub and the way you're seeing now, but the fact is that with a clock we need a real we need a fake clock, not just a stub. A fake, the difference between a fake and a stub is a stub returns hard-coded values. A fake actually tries to work just like the real thing. And we've been getting away with embedded stubs for most of our nullable infrastructure wrappers. And in most cases, you can do that. But in the case of a clock, the set timeout logic is really complicated. We need it to work fairly realistically, and for that we need a fake. And because I'm too lazy to build that myself, I'm going to use a third-party module. Also, it's complicated. I don't want to try to build that myself. So we can do a fake timers module from sign-on, which will require like this. Okay, and then down here, we can say our fake is equal to fake timers dot create clock, like this. And then for our date, we can just say that our date is equal to the fake date. And there we go. Okay, so we're defaulting now to 0. I think it's also nice to be able to configure our nulls. So let's go ahead and say that it can allows now to be configured. Configure now to be 42 because that is the answer. And expect that now should be 42. It's not, but that's easily fixed. We'll just take those options here, pass them through to our null globals here, and then here in our null globals, we'll destructure it, default it to 0, and make the whole structure optional. And then we can pass now into our create clock from sign-on. By the way, if you're interested in this, you can get it from GitHub. Sign-on.js fake timers. It's a very nice little library. It's got all kinds of stuff available on it. We're not going to be using most of it. Okay, that's the ability to configure our now. Now we're also going to need the ability to advance the clock. Just if we say wait, if we tell our fake clock or our null clock to wait, it's just going to hang because nothing's going to be telling the clock that it needs to advance. So we can say that it can advance the clock. So create null. We'll wait for that clock to advance. And we're going to have to put this, because our null, our embedded stub is not exposed to the outside world, we're going to have to put this on the public interface. And this is, I think, a bit of ugliness associated with using the nullable infrastructure wrapper. To make that excruciatingly obvious to the callers, I'm going to call it, rather than saying advance async, I'm going to call it advance null async. And you'll see what I'm talking about in just a moment. So we'll advance the clock, and then we'll assert that the clock's now is equal to 10. I thought about predefining now, but I think this is clean enough. Now this is going to fail. We don't have an advanced null. And in order to implement this, we do have to put it on the public interface, which again, that's a bit of ugliness. I don't love it, but all in all, I think that the ugliness we get from doing this is less than the ugliness we get from using another approach to dates. So I think it sort of pencils out in our favor. Other people would disagree though, and if you disagree and would rather use something like a mock, that of course is just fine. So advanced null async, we will just wait for advanced null async, which is not a real global, but we're going to pretend it is. Now this is still going to fail. We do not have advanced null async yet, but down here we can implement it. And the way we do that is we tell our fake timer to tick. And there we go. Now this is a problem because now if somebody in production codes calls advanced null async, the code's going to fail, and it's going to fail in an ugly way. So we want that to fail fast. So we're going to fail fast when attempting to advance the system clock. Now we could implement this so that the system clock, when you call advance async, it would just do the same thing as wait async, and that would be nice in a way. It'd be cleaner, but at the same time, I think it's an error for the system clock to be advanced. And I like my code, when there's a programming error like that, I like it to fail really visibly. Otherwise, those little programming errors tend to sort of stack up, and then they lead to bigger problems down the road. So but on the other hand, if you find this ugly and you do want the advanced null async to work for real in production, you could program this so that it works like calling set timeout. But I'm going to have it fail fast. So we'll make a real clock, and then we'll await, we'll assert that throws. And again, for those of, I mentioned this in past episodes, but if you're just catching us this time, this throws async is not part of chai, which is the assertion library we're using. So make sure you're using our wrapper around chai if you're trying to follow along. So we're going to ask the clock to advance null, and then we're going to see a failure. Can't advance the clock because it isn't a null clock. Charlie Pancake says no time travel allowed. Yeah, we have to do boring time travel, 1 millisecond per millisecond. Okay, it's failing. We're not getting the failure, but we can add that to our globals that we're passing in here. We'll just make our advanced null async, and we'll have that throw a new error. Can't advance the clock because it isn't a null clock. Hopefully I got that right. I did. Good. Okay, so now we've got the ability to get the current time. We have the ability to advance the clock when it's null. Last thing we need to do here is have some way of nulling out our timeout or our wait. So it can wait. So we need our null clock. We're going to wait for it. And we'll wait for 10 milliseconds. And that's going to fail because set timeout is not a function. I'll go ahead and add set timeout. And that is going to take a function and some number of milliseconds. But I'm not going to implement it yet. So that is causing our code to just hang because we're awaiting it. But here's the problem. Even if we implement this, wait async is always going to hang. In fact, I'll prove this to you. I'll implement it by calling the fake set timeout. That's what it takes to implement this. Our code's still going to hang. And that's because we're dealing with a null clock here, and the null clock is deterministic. It does not advance the clock until we tell it to, but we're not advancing the clock. So how are we going to do this? Well, what we're going to need to do is wait for the clock, but not get a result back. Now, in a perfect world, what we do is we'd say something along the lines of our wait promise is such and such. We'd assert that the wait promise is not resolved. Then we'd advance the clock. And then we'd assert that it is resolved. But in JavaScript, there is no way to tell if a promise is resolved or not. So we've got to be a little bit more clever. What I'm going to do is I'm going to set a variable. I'm going to call it wait status. I'm going to set it to waiting. And we can assert that right now the wait status is waiting. And it's complaining we don't have an await. I'll just make the linter happy for a moment. So there we say it's waiting. And then we're going to advance the clock. And let's advance it 20 milliseconds. And now we want to assert that the wait status is that, let's say we want to know when it's done. So it should have been done after 10 milliseconds. In order to do this, we need to have the wait async promise when it's done, run some code. Specifically, we're going to change the wait status to be equal to clock.now. And that will have to be non-constant. And we'll do it that way. And there we go. So a little bit complicated, but not too bad. Let's just call this wait. And there we go. We now have a clock that can wait, and we can have a clock that is nullable. I think that's done. I'm going to go ahead and check that in. Now we get to use this in our code. So let's go ahead and set this aside. We'll open up our countdown. So right now all this does is when we run it, it gives us to do. What we needed to do is we needed to take this array of text, print out one line at a time, and wait 1 second between each line. So let's go ahead and implement that. Let's say that it writes one line at a time, waiting 1 second after each line. We'll need some text. I'm going to go with something really simple because that will make it easier to debug. And then we'll run our countdown. And then we'll say countdown async. We'll pass in our text. And we need to be able to assert. And the first line is going to come out right away. So we can just assert that right away. We can assert that we're getting something from the command line. Let's say get last standard out. And it should be a 3. Of course, we'll need a command line. Command line, of course, is our command line, our null command line wrapper, our nullable command line wrapper. Take that, we'll pass it through into our countdown. And that fails. We're getting to do, but we expected 3. This is working because it's using our command line wrapper in the production code. Here, of course, rather than saying to do, we'll write out the first line of our text. And there we go. Now to introduce the clock, we'll need a null clock. We'll need to require it. Thanks for the question, Charlie Pancakes. So I'll get to that in just a second. And we'll need to pass that into here. Then we're going to advance the clock. By 1 second. We'll need to not wait for this. And then we'll assert that we get the next thing. That's going to fail. We're expecting 3, but we got 2. Here, we're going to need to get our clock. We'll default that to a real clock. We'll need to require it. Now here, if we just wrote the next thing without waiting, our test would fail. And the reason is that these would both run back to back. So this first test right here, this first assertion on line 18, that will fail because the most recent output will actually be 2. You can see that here. See, it failed on line 18, gave us a 2 instead of a 3. So to solve that, of course, we need to actually wait. for 1 second. Okay, there's been some comments in the chat. Charlie Pancake says, so you have to now make sure that nobody ever calls set timeout in production code. Is that a communication issue, or can you enforce it programmatically? And then Pellet says, you could probably monkey patch set timeout to warn folks about unintentional use. But as Charlie Pancakes mentions, that could affect dependencies. So yeah, I think you're right, Charlie Pancakes. We do now have to enforce that people use our clock wrapper rather than calling set timeout directly. But that is true for all infrastructure. It is always possible for people to call out to infrastructure directly. What we need to do is, as a team, establish a coding convention that whenever you want to use infrastructure, and that includes the clock, it includes random numbers, it includes anything external to our system, any sort of global really should be considered infrastructure. That we just want to establish a pattern of using the infrastructure wrapper. If you're using collective code ownership and pairing, you'll find that that's not really a problem to enforce. If you're using individual code ownership and no sort of code reviews, then yeah, you've got a potential problem. But generally, I don't find it to be an issue on the teams I work with. But again, they do use pairing or mobbing, or at least code reviews, and they use collective ownership. So everybody's touching all the code. Even if a mistake like that gets into the code, it doesn't last long. Collective code ownership is the idea that everybody is responsible for all the code, and people work on whatever part of the code needs to be worked on right now, not just the part that they originally wrote themselves. So it ends up with everybody on the team touching all parts of the code eventually. Pellet does say that you could, it seems like you could enforce it with a custom linter. Yeah, I think you could. In fact, even a non-custom linter, ESLint has the ability to make custom rules, I think. So you could use something like that. Personally, I haven't had it be a problem, so I wouldn't worry about it until it actually was a problem. Okay, we're pretty close to being done here. We've got the first two done. Let's go ahead and do the next one. We're going to wait for the one to come out. And of course, that's going to fail. So now let's do this in a not dumb way. We'll use a for loop. And I'm using a for loop rather than for each because of the await, which doesn't work properly with for each. And I believe that will work. Oh, what did I do wrong? Oh, and there we go. Let's look at this. Can we clean this up in any way? Yes, let's do it this way. Let's take this and make it a method. We'll call that advance 1 second async. Okay, that's I believe that's our application. Simple little toy application, but I think it's done. Let's see if it actually works. So we'll run it, and we'll expect to get one line at a time using the text that I've pre-provided in the run application. And there we go. As usual, works the first time, pretty much every time. And do notice that if we were testing this without controlling the clock, where we actually had to wait 1 second, our test would be really slow. And again, it would be unreliable because it's not going to be exactly 1 second after each line. It's going to be about 1 second. But how long that is, well, that can vary. By using the nullable clock, now we have total control over it. I do see a couple more questions, but I'll take those in just a moment. Before then, a couple of quick announcements. First off, the next episode is going to be next Tuesday at noon Pacific, same as usual. That's going to be July 21st, I believe. And what we're going to be covering is the second half of Flaky date-based tests, which is internationalization. internationalization. We're going to look at time zones and locales and rendering text. So don't miss that, July 21st at noon Pacific. And also I want to remind you that if you liked what you saw today, I'm very happy to do this sort of training or other sorts of consulting for your company. Go ahead and send me an email at jshore@jamesshore.com. Set up a free consultation to talk about what's going on with your teams and how I might be able to help. All right, there's some, happy to take additional questions or comments if there are any. Go ahead and put them in the chat. In the meantime, I think I'll start with Uncle Scientist because Pellets looks like it's on a slightly different topic. Uncle Scientist says, how do you test that the code doesn't wait until after the last number is printed? Well, we could, if we wanted this to not wait, which actually I do, because this is actually only one half of the toy example. The second half is to actually write out the time, but that's something I'm going to wait for until next week when we deal with internationalization. But if we did want to change this so that it wasn't waiting after the last second, what we could do is we could assert that the clock's time at the end was exactly what we expected it to be, which would be, I guess, just 2000. Now this is going to work. This test will pass, I think. Yeah, it does. And that's because we aren't waiting for this countdown async promise to complete. So we'd also need to get this countdown promise and await the countdown promise. And this, I think, will cause our test to hang right now because we're not advancing the clock. Yeah. So to fix this, we need to do this and then write out the last line. I think that will do it. Yeah, it's just kind of ugly, which is why I didn't originally specify the code to work this way. I don't really like the way this works, but this doesn't come up that often. I think we could make it a little cleaner. There is the ability in sign-on, I think, to advance the clock as far as you want. So we could advance it basically until the timeouts were all done and then check that the time was what we need it to be. But that would mean modifying the clock, so I'm not going to do that right now. I'm going to put this back because I want to check in the finished result that matches the specification in the README, which does say that we want to wait 1 second after each line no matter what. Okay. Thanks for the question, Uncle Scientist. Now, Pellet says, maybe off topic or better question for end of stream. Well, here we are. With collective code ownership, how do you avoid issues with having too many folks that you have to try to convince to try something? I have issues with a large team where it's hard to get folks on board for any initiative because everybody can say no to a change, but nobody can say yes without a dedicated tech lead or architect. I think that's a real issue. And I don't have an easy answer for you, Pellet. The fact of the matter is that if you're going to do something like collective ownership or even test-driven development, you kind of need everybody to be on board. Even test-driven development, if only a couple of people on the team are on board with it or on board with writing tests in the first place, what you're going to have is the people who aren't writing tests or the people who are doing test after, which tends to lead to lower quality tests. They're going to start breaking the code of the people who are doing tests. And that's just not a lot of fun to be in. So you do need an environment where people can agree on the practices that you're using. What I find is that you can have, if you have somebody who's just somebody that everybody looks up to, you can convince that person and get them to sort of lead the charge. You can also, something that I find helpful is to ask people to try something for a certain amount of time. Let's try this for a month and then decide at this date, on this time, in this meeting room, if we're going to keep doing it. It's much easier to try something than to commit to something long term. So that can also work. Another resource for you is a book called Fearless Change and More Fearless Change. There's 2 different books there by Mary Lynn Manns and Linda Rising. They have a bunch of different patterns for introducing new ideas to an organization that might be helpful for you. So, but other than that, yeah, I would agree. If you can't get people on board, then you just can't do it. And that's a situation where either you can find, you can either convince people to work the way that you enjoy working, or you can find a place that works the way you already know you enjoy working. And honestly, it's easier to change to a different company than to convince a lot of people of something they don't want to do. I do it in my consulting by doing the, hey, let's just try it. But I also have the virtue of coming in from the outside and being sort of a, bringing in, people always have more respect for people who they don't know. And I often, when we don't have a global pandemic, I often fly through the air, and people who come from a long way away are also listened to more than people who are close by. It's just one of the reasons to hire a consultant, sadly, is not necessarily that they have better ideas, but that people are more likely to listen to them. Yeah, Pellet says, my solution was to get under other projects. Honestly, that is the easiest way to do it. Find people who work the way you want to work. Charlie Pancakes says, proving my theory that the hard part of software development is the human/communication side. Always, always true. So true. All right, that is our time for today, or that is the end of our session for today. Thank you very much for watching. Once again, what we have done here is we have looked at flaky tests and how to prevent them. Specifically, we want to avoid slow, flaky tests, and the way we do that is by controlling our clock. We control when the horizontal and the vertical. We control when the clock times out by using it by controlling the timeouts, using deterministic clock, and controlling now. And the way we did that specifically today was with a nullable infrastructure wrapper around clock and using Synon's fake timers. That is it for this time. Thanks very much. Again, next week, Tuesday, noon Pacific, we're going to be looking at internationalization, the other side of flaky clocks. Thanks very much, everybody, and I will catch you all next time.